The following truth table shows the functionality of the D flip-flop with enable and reset. As we can see from the truth table, there are four main outputs, or actions that occur. One action being no change, which results when the clock is a falling edge and reset is 0. The next action would be reset, which we get when R reset equals 1, and that is regardless if the clock is falling or rising edge. Whenever R equals 1, then Q equals 0. Again, rising edge, we have set, which occurs when there's a rising edge on the clock, and the enable is enabled, and D equals 1, meaning that Q equals D, so Q equals also 1. And then undefined, which occurs when there's a rising clock edge, enable is on, D is also 1, so a set is going to occur, but then we also see that R equals 1, meaning that reset, so it's undefined. So if we go here to the code that has been reflected in our main VHDL file, we're monitoring clock R and enable. We see that if R equals 1, regardless of the clock or enable, Q equals 0, Q9 equals 1. Then we also see that in the event, when there's a clock event, a rising edge clock event, and enable has been set to 1, then Q equals D, and not Q equals not D. Again, we're going to go to our test bench file and see how this is implemented in testing. So we define the component, map the signals to the component signals, and then here we change as we loop through the test and begin to step forward for a given amount of seconds or nanoseconds, we see that each input has cycled between its possible values, so 0 and 1, but for different time intervals, and this allows for overlap of the inputs, resulting in a variety of combinations, so you can see all of the outputs possible. So if you go to the waveform, we're going to go ahead and step through a few times just to see what happens, and then I'll walk you through the actual waves. So we're going to skip the beginning part where they're undefined. We're going to start when they're defined. So right here, I'm going to zoom in. Right here we can see that the top one, clock, is 1, D is 0, reset also 0, enable is 1, Q is 0. So we don't notice any shift until Q, because we're waiting for a rising clock edge, enable, and D to be 1 or R to be 1. So we're going to go ahead to where Q finally changes. So here Q is about to change, and that occurs when, as you can see, clock is hitting a rising clock edge here. Data has been set to 1 further back, but data has been set to 1. Reset is 0, so that does not interfere with the system, and the enable is also set to 1. So when you hit that edge, then Q is going to match or represent the value of D. So let's continue forward. Let's find an instance where reset equals 1. So here, reset becomes 1. At this clock edge, it looks like everything sort of changes right here, so we'll examine that. Reset becomes 1, clock edge falls. Enable is still 1. However, because the clock edge is falling, that has no impact. The enable has no impact on the system, and also reset is 1. So regardless of the enable, as long as the enable, clock edge, and data are not all combined 1, then the reset will set the output Q to 0, which is what happens here. So we'll move on to one other instance of Q being impacted. Here, Q is shifted to 1, we see that there's a rising clock edge, so we monitor for that. D is set 1 further back, but is 1. Reset is 0. Enable is also 1. And so when that occurs at this clock edge, then they all switch.